Hello everyone, I'm going to present our research in freehand imaging systems. Freehand systems are based on moving a compact device by hand while its position is being tracked. Using this approach, the use of heavy positioning equipment can be avoided, which confers great flexibility to freehand systems. This is of special interest at the millimeter wave band due to the small size of the components at this frequency range, which can be easily integrated in general-purpose devices such as smartphones or tablets. Recently, we presented a freehand imaging system based on a compact radar-on-chip module using a monostatic configuration. This module was moved by hand while taking measurements to create a synthetic aperture. In this work, we extend the previous imager to a MIMO configuration, which allows us to significantly increase the acquisition speed and to improve the quality of the obtained images, which are updated in real time as more measurements are acquired. The use of a MIMO configuration gives us the knowledge of the relative position of the transmitting and receiving elements, which helps us to reduce the positioning errors. These errors are further mitigated with a calibration procedure that we proposed in this work. In summary, in this contribution, we presented a freehand imaging system based on a compact radar-on-chip module using a MIMO configuration, which is capable of producing high-resolution images at a fast acquisition rate.
Hello, everyone. It is a great honor for us to share our recent progress on microwave computational imaging, MCI. In this video, we will introduce our research on a frequency-diverse bunching metasurface antenna, FDBMA, designed to enhance the performance of microwave computational imaging systems. In conventional microwave imaging systems, reconstructing an image requires just scanning the scene point by point. In contrast, Metasurface-based MCI encodes the scene with pseudo-random radiation patterns, and the backscattered data is compressed into one channel. It is a typical inverse scattering problem, and it can be solved using compressive sensing algorithms. This method significantly enhances imaging performance while reducing hardware complexity. However, metasurface-based imaging is limited by the number of measurement modes and the SNR of detected signals. To overcome these limitations, we combine a disordered cavity with an optimized high-dispersion metasurface to increase the number of measurement modes. And we propose a novel joint bunching method to enhance the SN level by increasing the directivity of pseudo-random radiation patterns. As shown in the figure, both the disordered cavity and random metasurface can generate frequency-diverse patterns with frequency intervals of 100 MHz and 50 MHz, respectively. Combining these reduces the interval to 20 MHz, yielding more qualified patterns within the same bandwidth. The joint bunching method integrates the metal baffle, quasi-gradient random metasurface, free non-dielectric lines, and random coherent superposition methods. This approach improves the directivity of radiation patterns while maintaining a correlation. This method is general, and it can be applied to various metasurface antennas for practical microwave computational imaging. We validate our design through imaging experiments. Using the fabricated FDBMA as a transmitter and the probe as the receiver, we place an X-shaped targeting imaging plane. The experiments have three parts. First of all, we validate that the SN of the detected signal has an impact on the quality of reconstructed images. High-fidelity reconstructions can be achieved with an increased SN level. Then, we demonstrate the advantage of reducing the frequency interval. Comparing 41 and 201 measurement modes, we find that more measurement modes produce better images under the same conditions. Finally, the advantage of the bunching design is verified. Increasing the imaging distance from 0.5 meter to 1 meter, the bunching design maintains image quality, unlike the non-bunching design, which observes a drop to decreased SNR. Thank you for watching. For more details, please refer to our paper. Cheers!
This page shows the configuration of the STCMA. The antenna consists of two arrays of plus or minus 45 degrees orientated slot openings on the top of a substrate integrated waveguide, SIW. Each slot opening contains two pin diodes that switch the element between the radiating and non-radiating states. We show that the STCMA can achieve NFF at the fundamental frequency. The STCMA can be viewed as a type of LWA that progressively leaks energy from the waveguide into free space. To realize high directivity pencil beam radiation, the amplitude envelope of an amplitude modulated AM LWA should follow the sinusoidal waveform. To achieve NFF, the amplitude envelope should be generalized into the following equation. To realize Y-polarized radiation, the radiated waves from the two plus or minus 45 degrees orientated slot arrays should have identical amplitude yet 180 degrees phase difference. Therefore, the envelopes for plus or minus 45 degrees polarization should be as follows. The desired amplitude envelopes can be practically implemented by using the time average effect of the spatiotemporal modulation. Here show the corresponding 1-bit STC matrices that describe the slot elements' radiating/non-radiating states in space and time domains. We use FPGA to program the antenna for encoding the operation of meta-atoms and finally realize software-defined automatic NFF scanning. Here we show the measurement results of NFF beam scanning compared with simulations. As observed, measured results are in good agreement with simulated ones. The FWHM of the focusing beam directly determines the resolution of the imaging system. This page shows the configuration of the proposed imaging system. The STCMA and an open-ended waveguide function as the transmitting and receiving antennas, respectively. Every time a new STC matrix is loaded into the metasurface via FPGA, a corresponding new focusing beam is formed accordingly. In our experiments, 64 states of meta-atoms are designed to generate sequential focusing beams. The required STC matrices are programmed into FPGA and will be loaded upon external triggering to achieve automated beam scanning. The scattering field is utilized as the primary indicator for scene mapping. MATLAB scripts are executed to enable communication and synchronization between the metasurface and VNA, facilitating the automated and dynamic refreshing of scattering field data for real-time sensing. A conducting rod, 10 mm diameter, 100 mm long, is measured for system calibration. A calibration procedure is carried out to eliminate the effects of scattering from the surroundings and mutual coupling. A compensation model is applied to the calibrated data to counteract the inconsistencies of the emitted beams. A subwavelength conducting rod, oriented parallel to the y-axis, functions as the point scatterer for PSF evaluation. The object is translated along the x-axis in the focal plane, and the corresponding PSFs are measured, respectively. The resolution ranges from 8.94 mm to 13.65 mm. The spatial resolution is constrained by the Rayleigh criterion. Comparison of the theoretical resolutions and measured ones reveals close agreement, demonstrating the capacity of the proposed imager to resolve two objects at distances of 1014 mm at 22.5 GHz. The STCMA is capable of conducting a beam scanning of 64 states within 1 millisecond, facilitating real-time dynamic detection and imaging. The entire imaging process primarily consists of communications among the VNA, STCMA, and MATLAB, as well as data acquisition and post-processing, which consumes approximately 0.2 seconds. The imager enables real-time dynamic 1D imaging at a frame rate of 5 fps. The current imager is confined to conducting 1D imaging solely in the x direction. By integrating the x-axis electronic and y-axis mechanical scannings, the imager is now equipped to accomplish 2D imaging on the xy plane. A MATLAB script is developed to ensure the fully automated operation of the entire process described above. A test sample has been prepared to validate the imaging performance of this approach. The entire imaging process, including 1472 measurements and data post-processing, can be accomplished within 15 seconds. The imaging result is in good agreement with the ground truth. Given the same configuration, this modality possesses the capability to accomplish rapid imaging and detection in more scenarios, including dielectric objects, hidden targets, and fissures within objects.